quiet afternoon in eastern Canada, a sudden shudder under Ottawa. Walls move, dishes rattle. A rumble rolls from Quebec to Toronto to Montreal in under a minute. It measured only a 4. Scientists call it minor. They are still deeply uneasy, because this ground is supposed to be still. The Canadian interior is locked inside one of the most stable continental plates on Earth, yet tremors keep arriving. A January shock near Orillia, an April strike near Shoreville. 2 warnings in a region that barely speaks. Stay with me. You will see an ancient buried rift under Ottawa, ice from the last ice age still twisting the crust, and a silent fault beneath Vancouver Island that has not released in 300 years. If this grips you, hit like and subscribe. It helps. We are just getting started. 12:36 in the afternoon, April 14th, 2026. A loud crack rolls through the hills of western Quebec. Inside homes near Shoreville, ceiling lamps sway. Windows buzz in their frames. Dogs freeze mid-step. And somewhere deep below the Ottawa River Valley, a piece of rock that had been holding still for decades finally gives way. The United States Geological Survey catches it first. Earthquakes Canada confirms it seconds later. Magnitude 3.9. Depth around 10 kilometers. Epicenter 20 kilometers north-northeast of the small Quebec town of Shoreville, just across the provincial line from eastern Ontario. It sounds like a small event. It is not. Within minutes, the "Did you feel it" system at Natural Resources Canada starts lighting up. Reports pour in from Ottawa, from Gatineau, from Pembroke, then from farther away, Montreal, the Laurentians, suburbs of Toronto more than 300 miles from the epicenter. People in office towers describe a rolling motion. Drivers on rural roads say their trucks rocked. Construction crews working on bridges across the Outaouais stop and look at each other. This was the moment a region that rarely speaks suddenly spoke. Here is what matters. Eastern Canada is not the Pacific coast. It sits near the center of the North American tectonic plate, far from the boundary where plates collide. Physics textbooks call this intraplate territory. Stable, old, cold, rocks that have been cooling for more than 1 billion years. And yet at 12:36 in the afternoon, the ground shook hard enough to be felt across multiple provinces. That distance is the first clue that something unusual is happening under our feet. In the hours after the quake, Canadian seismologists did what they always do. They checked the seismograms, they estimated depth, they ruled out industrial activity, they cross-checked with the USGS. Everything pointed to a natural tectonic event inside the western Quebec seismic zone, the long band of ancient faults that stretches from Montreal up the Ottawa Valley toward Temiskaming. No damage was reported, none was expected. The magnitude was too modest for that. But damage was never the story. The story was the location. The story was the timing. Because this was the second felt earthquake inside the same broad zone in under 3 months. And the previous one, in late January near Orillia, had already caught scientists off guard. 2 shocks in 2 places that almost never shake, separated by 77 days, inside a region that statistically should produce one of this size every 5 to 10 years. Something in the numbers had shifted. That afternoon, phones in government seismology labs in Ottawa kept ringing. Reporters wanted explanations, residents wanted reassurance, researchers wanted data. And under it all, one question started to repeat in the background of every call, quietly, carefully, the way scientists phrase things when they are not sure yet. Why here? Why now? And why again? standing above a buried fault line on a spring afternoon, most people will never feel anything. On this day, millions did. A tiny release of energy in a place that should be quiet reminded a country that the ground under Ottawa has memory, and memory in geology is almost never empty. To understand what the Shoreville shock is really telling us, we need to go deeper than the tremor itself. We need to look at why this region shakes at all. A magnitude 4 in eastern Canada is not the same thing as a magnitude 4 in California. That simple sentence is where the real story begins. In the Pacific Northwest, a shock of this size barely registers in public memory. In Tokyo, almost no one stops their lunch. On a soft seabed off South America, the waves of energy die out quickly, swallowed by broken water-filled rock. Energy goes in, energy gets absorbed. The shaking fades within a few dozen miles. Eastern Canada behaves differently, and the difference comes from the rock itself. Under Ottawa, Montreal, and much of Ontario and Quebec, the crust is part of the Canadian Shield. This is some of the oldest, hardest, driest stone on the planet, built up from roots of mountains that existed more than 1 billion years ago. It is cold, it is dense, it has almost no fluid, and when a seismic wave enters it, the rock does not absorb the energy the way softer, younger crust does. It carries it, long distances, almost like a bell. That's why a modest Shoreville quake was felt in downtown Toronto more than 300 miles away. That is why a lightly felt tremor near Orillia in January reached Niagara Falls in the south and Belleville in the east. The magnitude was small, the reach was large. Seismologists have a short way of describing this: Eastern Canadian crust rings. Now think about what this means for a modern city sitting on top of that bell. In Western regions, buildings are engineered with earthquakes in the foreground of every blueprint. Base isolators, steel frames, retrofitted bridges, tsunami maps on refrigerator doors. In much of Eastern Canada, buildings and infrastructure were not designed with the same seismic assumptions. The Ottawa Valley has dams, it has nuclear stations within regional reach, it has 19th century stone churches in Montreal, it has bridges that span the St. Lawrence and the Outaouais, and it has millions of people who have never practiced a drop, cover, and hold-on drill. A magnitude 4 passes over all of that as a rumble, a magnitude 6 does not. The historical record proves this. The 1935 Temiskaming quake, deeper in the same western Quebec seismic zone, reached magnitude 6.1. It cracked chimneys, split walls, and was felt from Manitoba to Virginia. It happened in a region that, for decades, had been classified as calm. One moment everything was still. The next moment the bell rang hard enough to damage buildings 1,000 miles away. This is why scientists treat small tremors in eastern Canada as signals, not shrugs. A magnitude 4 tells them the system is alive. It confirms that stress is moving along ancient faults. It tells them certain zones inside this quiet landscape are still active enough to nudge rocks into slipping. It does not tell them the next shock will be bigger, but it does not rule it out. Here is the harder question still waiting under the surface. If the rock rings and the faults still move, what is actually doing the pushing? In a region far from any plate boundary, what force is squeezing the crust hard enough to crack it? The answer goes back 1 billion years, and to find it, we have to look at a scar that almost no one in Ottawa realises is directly beneath them. Late on the night of January 27, 2026, most of southern Ontario had already gone to sleep under a heavy week of snow. At 10:59, the ground moved. Not dramatically, not violently, a sharp thump, a low growl, a brief swaying of light fixtures across the Greater Toronto area, magnitude 3.7 according to Earthquakes Canada, magnitude 4.1 according to the United States Geological Survey, depth around 5 kilometers, epicenter 23 kilometers southeast of the small Ontario city of Orillia, about 99 kilometers northeast of downtown Toronto. Within hours, 2,600 people filed official reports that they felt it. That number kept rising for days. Residents in Kingston felt the rumble from nearly 200 miles away. People in Kitchener felt it to the west. Reports came in from as far south as Niagara Falls, from Belleville to the east, even from parts of the Greater Toronto Core. For a shock that size, the reach was extraordinary. But the location was what made seismologists pause. This was not the Western Quebec seismic zone. This was not Charlevoix or Ottawa or the St. Lawrence corridor. Orillia sits inside a swath of central Ontario that is statistically among the quietest pieces of continental crust in North America. In the previous 40 years, only one small earthquake above magnitude 2.5 had been recorded near that exact location. Nothing close to this. Earth scientists at Western University and the University of Toronto called it rare. Seismologist Marika Adams at Natural Resources Canada reminded the public that Ontario sits deep inside the North American plate, where earthquakes are infrequent and the causes are harder to pin down than on the West Coast. Her team described the likely mechanism in careful language: regional stress, old buried faults, zones of weakness in the crust reactivating under quiet but steady pressure. Then came the strangest part of the coverage. Some Canadian scientists pointed to a source of stress most listeners never imagine when they think about earthquakes: ice. More specifically, ice that vanished more than 10,000 years ago. Science and technology communicator Dan Riskin told a national audience the same afternoon that the Orillia shock could be connected to the slow aftermath of the last ice age, when a glacier 2 miles thick finally lifted off the Canadian crust and the rock underneath began to rise. That is not science fiction. It is active research, and it is a mechanism we will come back to. For now, notice what January handed us: a rare tremor, an unexpected location, a wide felt area out of proportion to its size, and a range of causes that all pointed in one uncomfortable direction. The interior of Canada is not as quiet as most people assume. Then, 77 days later, the Shoreville quake hit. Different province, different zone, same general message. Something under eastern Canada is releasing small pulses of energy in places that should, on paper, be almost silent. 2 events. 2 seismic zones, one uneasy pattern forming. To see what is actually feeding these tremors, we have to descend beyond the modern landscape. We have to read the scars of a continent that was once pulled apart by forces most people have never heard of. The phrase stable continent hides an enormous secret. The interior of North America is not still. It is squeezed. Every day, invisible forces press on the bedrock beneath Canada. Some come from plate collisions thousands of miles away. Some come from the weight of ocean water loading the edges of the continent. Some come from the slow upward push of hot mantle rock rising under North America. And some come from the departure of an ice sheet that pressed this land down so hard, the crust still has not finished bouncing back. Add these forces together, and you get a very specific kind of landscape. From the outside, calm. From below, loaded. The main source of horizontal squeeze is the ridge in the middle of the Atlantic Ocean. Hot rock rises along that ridge, cools, and pushes outward. This push is called ridge push. It shoves the entire North American plate westward at a slow, steady rate. That force does not stop at the coastline. It travels through the crust, through the Appalachians, through Quebec and Ontario, all the way to the Rocky Mountains. Canada sits inside that traffic. Now layer in the other forces, the Pacific Plate grinding into western British Columbia. The slow rotation of the continent as a whole, the last remnants of an ice age deformation, the heating effects of ancient mantle plumes that still warm the base of the crust in some regions. Every one of these forces contributes to a background field of stress. In most places, the bedrock is strong enough to absorb this stress without breaking. The quartz, the granite, the ancient metamorphic rock beneath the Canadian Shield can hold enormous strain without slipping. This is why the continent feels quiet, but quiet is not calm. Whenever a piece of old crust carries an existing crack, a buried fault, a weakened zone from an ancient rift, or a fractured edge left over from a mountain range that eroded away hundreds of millions of years ago, stress can concentrate there, slowly, invisibly, over centuries. Then one day the weak zone gives. This is the core definition of an intraplate earthquake. No colliding plates directly underneath, no volcanic heat pushing upward, just accumulated pressure finally exploiting an old scar. The scar might be older than the dinosaurs. The scar might have been silent for thousands of human lifetimes. And when it moves sharply, because the rock around it has been cold and brittle for a very long time. Eastern Canada is full of these scars. The Ottawa Valley carries one, Charlevoix carries another, the St. Lawrence Corridor carries a chain of them. Large parts of northern Ontario carry more, quieter, but still detectable. Every time a small intraplate quake hits one of these zones, it reminds seismologists that the stress field is still there, still pressing, still patient. When you hear that the January Orillia shock and the April Shoreville shock happened in quiet regions, picture that hidden field. Picture a continent under constant slow pressure. Then picture hundreds of old fractures spread across it, any one of which could release a burst of that pressure if the conditions line up. The ground above does not show it, the seismographs do, and the oldest, deepest scar under eastern Canada starts right beneath the capital. Walk across Parliament Hill in Ottawa, and you're standing almost directly above a rift that tried to tear North America apart 1 billion years ago. It failed. It healed. It went silent, and the faults it left behind are still there, still waiting. Geologists call it the Ottawa-Bonnecher Graben. The word Graben means trench. It is a long, narrow block of crust that dropped down between two parallel faults when the continent was young. From the air you can trace its shape. It runs northwest to southeast across eastern Ontario and western Quebec, following the path of what is today the Ottawa River. Mountains framed it once. Deep fractures anchored it. Then the rifting stopped, and the graben became a quiet seam. Here is what quiet really means. The rock in and around the graben is older than the oldest fish in Earth's history. The faults cut down through the crust for miles. And even though they stopped creating new mountains long ago, they remain zones of weakness. Seismically, they are like cracks in a very old window. The glass still works, but it breaks faster along the crack than anywhere else. Modern researchers have been mapping these cracks in detail. A 2021 study in the journal Earth and Space Science used stress models to examine which faults in the western Quebec seismic zone have the highest potential to slip under today's pressure field. The Timiskaming Fault, the Cross Lake Fault, the Montreal River Fault, the Latchford Fault, and several unnamed faults near the epicenter of the 1935 magnitude 6.1 Temiskaming earthquake. All showed what scientists called relatively high reactivation potential. That phrase is worth slowing down for. It means those ancient cracks are still oriented in exactly the wrong way for the modern stress field. They can slip, they can release energy, they can produce earthquakes, and this is not theory. In 2013, a magnitude 4.7 quake called the Ladysmith event struck close to the Graben. A follow-up study calculated how that shock transferred stress to nearby faults. Parts of the system became slightly more loaded, not less. The pressure did not disappear. It shifted to the next crack in the window. Now think about what happened on April 14th, 2026. The Shoreville quake struck close to the same long corridor of ancient faults, not far from the zone where the Ladysmith shock occurred. It was small. It caused no damage, but it was another pulse along one of the most seismically persistent scars in eastern Canada. One more pressure release along an old trench that never fully closed. The Ottawa-Bonnequer Graben is not about to split the continent again. Rifting stopped hundreds of millions of years ago, yet inside this narrow band of crust, the history of earthquakes is unmistakable. A magnitude 6.1 in 1935, a magnitude 5.7 in 1944 near Cornwall and Messina, smaller events every few years, and a growing list of quakes in 2026 that suggest the system is neither dead nor sleeping. A city of 1 million people grew up on top of this graben. Government buildings, universities, hospitals, museums. Most residents have no idea what lies under the Ottawa River, but there is another older graben just to the north, and its historical record is even more uncomfortable. North of the Ottawa River the land changes, lakes stretch between forested hills, highways thin out, small Quebec and Ontario towns appear and disappear along winding roads. Underneath all of it runs another older rift, the Temiskaming Graben. It is deeper than the Ottawa-Bonnequer Graben. It is more obvious on geological maps, and its earthquakes have been louder. On the night of November 1st, 1935, the earth above this rift tore violently enough to be felt across parts of 11 American states and 5 Canadian provinces. The shock measured around magnitude 6.1. It cracked chimneys in Ontario mining towns. It knocked dishes off shelves in Toronto 400 kilometers away. It rattled buildings in Washington, D.C. It killed a horse, damaged bridges, and left residents of Temiskaming describing a sound like artillery fire rolling through the forest. It remains one of the largest earthquakes in modern Canadian history, and it came from the same seismic system that produced the April 2026 Shoreville shock. The Temiskaming quake is a warning carved into the scientific record. Before it struck, the region had no reputation for violent earthquakes. The surface was calm. The buried faults had been silent within living memory. Then one night, a piece of ancient crust slipped, and suddenly the quiet region was the site of a magnitude 6 shock large enough to be studied by seismologists around the world for decades. A 2023 study in the Canadian Journal of Earth Sciences took this event apart mathematically. The researchers modelled how the Temiskaming shock redistributed stress onto nearby faults. Their calculations showed that the 1935 quake produced extensive positive Coulomb stress change on its receiver fault, the word positive meaning loaded further toward failure. They also concluded that the aerial extent of those loaded fault zones suggests earthquakes with a magnitude comparable to the 1935 event can be triggered again. Read that slowly. The same system that produced a magnitude 6 in the past has been quietly pushed closer to producing one in the future. Now add the rest of the sequence. 1944 brought a magnitude 5.7 between Cornwall, Ontario and Messina, New York, inside the southern end of the broader western Quebec seismic zone. 1932 brought a significant event near Lac Kipawa. 2010 brought the magnitude 5 Val-des-Bois shock, felt from Detroit to Boston and right through the government buildings of Ottawa. 2013 brought the Ladysmith quake. 2026 has brought the Orillia and Shoreville shocks. The pattern is not regular. It is not predictable in any useful short-term sense, but it is consistent. This zone produces small to moderate shocks almost continuously, and every so often, one of those shocks is not small at all. The Timiskaming Graben has been described by researchers as a region of moderate, persistent seismicity with a capacity for large events. In plain terms, it is a wound in the continent that occasionally reopens, and the stress feeding it does not come from a nearby plate boundary. It comes from forces most people would never associate with earthquakes: ice, a ghost of ice. And to see it, we need to step back 10,000 years. The night of November 1st, 1935 began cold and ordinary in the mining towns and logging camps of northern Quebec. Then, at about 1:06 in the morning local time, the ground lifted. People described it as a bomb detonating underground, followed by a deep rolling motion that travelled through houses, bunkhouses, barns, and the bedrock beneath them. It was the largest earthquake eastern Canada had recorded since modern seismographs existed, a magnitude 6.1. Some older estimates placed it at 6.2. Either way, it was enormous for the region. The shaking rippled outward across a vast stretch of North America. Reports poured in from Ontario, from Quebec, from New York, Pennsylvania, Ohio, Indiana, and as far south as Virginia. Buildings swayed in Washington, D.C. Light fixtures moved in Boston hotels. The shock was felt across more than 2.5 million square kilometers, which is a remarkable reach for a moderate magnitude event. Why did this modest 6 reach so far? The answer is the same principle we saw earlier. The Canadian Shield carries seismic waves with stunning efficiency. A magnitude 6 in California fades inside a few hundred miles. A magnitude 6 in Canada travels. The damage in 1935 was concentrated near Temiskaming, a small town across the Ottawa River from Ontario. Chimneys collapsed, walls cracked, a rail line twisted, bridges suffered structural damage. The human toll was small because the region was lightly populated and the shock happened in the middle of the night, when most mines and mills were idle. If the same earthquake had struck today under a city of 2 million, the loss of life would almost certainly be counted in the hundreds. The 1935 event also rewrote what Canadian scientists believed about the region. Before that night, the geological consensus treated the Ottawa Valley as quiet. After it, every seismology paper about eastern Canada had to reckon with what had just happened. A magnitude 6 in an intraplate setting, along a scar most people had never heard of, in a country where nobody expected it. Alan Bent of the Geological Survey of Canada produced one of the most detailed studies of the quake decades later, in 1996. Using regional seismic waveform data, he refined the source mechanism. His results indicated the rupture happened on a steeply dipping fault, releasing energy at a depth of roughly 10 kilometers. That is the same depth range as the April 2026 Shoreville shock. It is the same layer of crust. It is the same kind of failure, just at a smaller scale. Scientific modelling has continued, a 2023 Canadian Journal of Earth Sciences paper concluded that the 1935 rupture transferred enough stress to nearby faults to nudge some of them further toward failure. A 2021 Earth and Space Science paper identified several faults, including the Timiskaming, Cross Lake, Montreal River, and Latchford faults, as holding relatively high reactivation potential under the present-day stress field. The Temiskaming earthquake is not a historical curiosity. It is a living reference point. It proves the zone can produce magnitude 6 shocks. It proves those shocks can reach major cities. It proves the mathematics that warn us another similar event is physically possible in the future. Now comes the deeper question. What exactly has been loading these old faults for all these centuries? The answer involves a weight that left North America long ago, but whose absence the crust is still adjusting to. 20,000 years ago, the region that is now Ottawa lay under a wall of ice more than 2 miles thick. The Laurentide ice sheet covered most of Canada and the northern United States, from the Rockies to the Atlantic. Its weight crushed the bedrock beneath it. The surface of the crust sank under the load like a mattress under a sleeping body. Then the climate warmed. The ice began to melt. Over thousands of years, that massive weight disappeared, and the bedrock that had been pushed down for tens of thousands of years began to rise. It is still rising today. Scientists call this process glacial isostatic rebound, or post-glacial rebound. It is one of the slowest, largest, most invisible shifts happening anywhere on Earth. Parts of Hudson Bay rise by as much as a centimetre per year. Parts of southern Ontario and Quebec rise much less, but measurably. Satellite tracking systems can detect it. Precise surveying confirms it. The continent is still remembering the ice. Now think about what that rebound does to ancient faults. A rising block of crust is not a simple thing. Different regions rebound at different speeds. Different depths respond differently. The forces inside the rock become uneven. Where once the faults felt uniform compression, they now feel changing stress patterns. Some faults get squeezed more tightly, some get pulled open slightly, some get tilted, and all of this happens to old buried faults that are already sitting inside a continent being pushed sideways by ridge push from the Atlantic. This is not speculation. It is a major area of research. Canadian geologist John Adams published a foundational paper in 1989 on post-glacial faulting in eastern Canada, documenting fault scarps that had clearly moved after the ice left. Modern LIDAR surveys have since mapped additional features in southern Quebec and northern Ontario that look like post-glacial ruptures. Some scarps stretch for kilometres. They are evidence that, in the thousands of years after the ice vanished, the crust broke violently in places, probably during large earthquakes triggered by the rebound itself. When Canadian scientist Dan Riskin told the national audience in January 2026 that the Aurelia shock could be linked to glaciers melting 10,000 years ago, this is what he meant. The mechanism is real, it is slow, and it is still active. Here is how to picture it. Imagine pressing your hand flat on a thick, springy foam cushion. The foam compresses. Now lift your hand. The foam starts to rise, but it does not rise all at once. The center lifts first. The edges follow later. Strains develop across the surface, and if there is a crease in the foam, that crease bends, opens, or stretches. The crust of Canada is still doing exactly this, slowly, silently, for thousands of years. What this means for our two recent earthquakes is subtle, but important. Some of the pressure that pushed the rock at Shoreville and Aurelia past its breaking point was not delivered yesterday. Part of it has been accumulating since the Ice Age. The events we call recent are small releases along a pressure system older than human civilization. And rebound is not the only long-lived force operating in this region. There is another, far stranger mechanism tied to a hotspot deep in the mantle. To see it, we need to follow a line of ancient scars across the ocean floor, stand on a beach on the shore of Hudson Bay, Canada, and look at the landscape around you. Something will feel subtly off. Old shorelines sit high above the current water. Gravel terraces climb up hillsides far from today's surf. Ancient beaches, with rounded stones shaped by long-gone waves, rest hundreds of feet above the modern coastline. Those beaches are the footprints of the rising land. 20,000 years ago, this region lay under ice more than 2 miles thick. The weight of that glacier pressed the crust deep into the softer mantle below. Imagine pushing a block of wood into a tub of thick honey. The wood sinks, the honey flows outward. When you lift the wood, the honey slowly flows back. The crust of Canada is the wood. The mantle is the honey. And after the ice left, mantle rock began a slow return journey beneath us that is still not finished. Hudson Bay is rising today by as much as a centimetre per year. Parts of northern Quebec are lifting several millimetres annually. Southern Ontario and southern Quebec rise more slowly, but still measurably. Global positioning satellites track it in real time. Tide gauges record it indirectly. Lake shorelines around the Great Lakes are tilting because the northern ends are rising faster than the southern ends. All of this motion generates stress. Different depths of crust rebound at slightly different rates. Different parts of the continent lift at different speeds. This uneven rise stretches some regions, compresses others, and twists the ancient faults that run through the Canadian Shield. The Western Quebec seismic zone sits on top of a landscape that is still adjusting. So does the St. Lawrence Valley. So do many of the intraplate zones across eastern Canada. The connection to earthquakes is direct. When a fault is already loaded by ridge push from the Atlantic and by regional stress from other mantle processes, a small addition from rebound can be enough to nudge that fault over the edge. The quake itself is a rapid slip. The loading is ancient. Scientific literature calls this mechanism glacial isostatic adjustment, and it appears throughout modern research on Canadian seismicity. Studies of the Charlevoix seismic zone, of the Western Quebec seismic zone, and of Eastern Ontario all consider it as part of the present-day stress field. It does not work alone. Plate motions matter. Buried faults matter. But rebound is a persistent companion, and it has not stopped yet. Now connect this to the 2 quakes that open this story. The January shock near Aurelia occurred along an old weak zone, in a region where rebound is active. The April shock near Shoreville occurred inside a rift system, where rebound stress combines with the ridge push along the Ottawa Valley. Neither event, on its own, is proof of anything dramatic. But each event fits neatly into a larger model that has been developing for decades. This is why Canadian seismologists keep paying attention to small tremors in regions that should be quiet. A magnitude 4 is not a threat, but it is a data point, and every data point fills in the picture of a continent that has been squeezing, lifting and cracking for a very long time. There is another ancient force working beneath eastern Canada. It is hotter, older, and stranger than rebound. It runs in a line across the ocean floor. A dead fault is a myth, or at least, it is a description most working seismologists avoid. What scientists actually mean when they call a fault dormant is that it has not been observed to move recently. The rock along the fault is cold and locked. Friction holds it in place. As long as the stress pressing on the fault stays below a certain threshold, it does not slip. It might stay quiet for centuries, for thousands of years, in some cases for tens of thousands of years. That does not mean the fault has healed. It means the conditions for slip have not yet arrived. Post-glacial rebound changes those conditions. Remember what rebound does. As the crust of Canada rises back up after the disappearance of the ice sheet, the strain field inside the rock changes. Faults that were sitting in one orientation of stress suddenly find themselves in a slightly different one. The squeeze across the fault plane may decrease, the shear along it may increase, the friction holding it in place becomes easier to overcome. That is how a fault that has not moved in 10,000 years can suddenly slip. The geological record of Canada is full of evidence that this has happened before. Researchers have mapped fault scarps, sharp steps in the landscape, along hillsides in eastern Quebec, northern Ontario, and parts of the Maritimes. These scarps cut through glacial deposits. They sit on top of features left by the retreating ice. That stratigraphy proves the faults moved after the ice was gone. In some cases, the scarps are tens of meters high, which implies surface rupturing earthquakes that would have been devastating by modern standards. Natural Resources Canada has studied these features for decades. John Adams, in his 1989 paper on post-glacial faulting, argued that the ice sheet loaded the crust, suppressed fault motion while the weight was there, and unleashed a burst of seismic activity once the ice was gone. Later studies have refined the timing, showing that the largest events likely happened within thousands of years of deglaciation, tapering off as the crust adjusted. Here is the uncomfortable implication. The adjustment has not finished. The numbers are still being worked through the system. Faults that have been quiet since the last glacial retreat may still be in a transition zone between locked and unlocked. Not every one of them will break. Many will continue to hold. But some, in the right orientation and in the right position in the stress field, can be pushed towards slip by additional pressure from ridge push, plate motion, or regional stress variations. This is why the modern tremor record of Canada matters so much. Each small event in a quiet region gives researchers a new data point. Where are the active scars exactly? Which orientations are slipping? How deep are the ruptures? How does the stress redistribute after each event? When the January Aurelia shock appeared in an area with only one recorded earthquake above magnitude 2.5 in the previous 40 years, seismologists did not panic. But they did not dismiss it either. It became a new pin on the map. A fault that was nearly silent had just spoken. When the April Shoreville shock struck along the western Quebec seismic zone, the pin on the map went right into the same ancient graben that produced the 1935 and 1944 quakes. That was not a surprise, it was a reminder. And there is another layer hidden inside this continent, a mantle scar that runs under Ontario and Quebec and deep out into the Atlantic. 5 past midnight on September the 5th, 1944. The St. Lawrence River shone dark under the stars. Farms, villages, and small border towns were quiet. Then the ground shifted under Cornwall, Ontario, and Messina, New York at the same instant. Houses rocked, brick walls split, chimneys collapsed. The shock rolled outward across 8 American states and 4 Canadian provinces. Magnitude 5.7. Some estimates place it at 5.8. It was the most damaging earthquake to strike eastern Canada in the 20th century outside of the 1929 offshore event, and it targeted a region that had almost no seismic reputation before it hit. The Cornwall-Messina earthquake is a direct warning that the southern end of the western Quebec seismic zone is also alive. The damage was concentrated along the international border. In Cornwall, Ontario, more than 2,000 chimneys were damaged or destroyed. Masonry cracked. Plaster fell. Schools, churches, and older buildings suffered structural harm. In Messina, New York, just across the river, insurance claims piled up for months. The total damage in 1944 dollars was estimated in the millions, a very large sum for a thinly populated rural region. Alan Bent of the Geological Survey of Canada analysed the source mechanism of this quake in a 1996 paper in the Bulletin of the Seismological Society of America. Using regional waveforms, he determined that the rupture occurred on a steeply dipping fault at a depth of roughly 12 to 18 kilometres. The direction of motion was consistent with the regional stress field. In simpler words, a buried ancient fault along the St. Lawrence corridor slipped in a pattern that matched exactly what the surrounding stress would predict. The fault was not random. It was loaded and ready. Here is the part that should not be forgotten. Before 1944, no one in Cornwall expected a damaging earthquake. There was no modern building code for seismic resistance in that part of Ontario. There were no public preparedness campaigns. There were no instruments in the area capable of recording the event precisely. When the shock struck, it revealed that a region which felt stable was, in reality, sitting on a fault with the strength to deliver a magnitude approaching 6. That revelation has aged poorly. The population along the St. Lawrence has grown enormously since 1944. Montreal has become a metropolis. Ottawa has become a capital of more than 1 million people. Cornwall, Kingston, Gatineau, and smaller cities between them have expanded dramatically. Bridges, dams, and energy infrastructure now line the corridor. If the Cornwall-Messina earthquake repeated today, the damage estimates would be orders of magnitude higher, and the human cost could be severe. Modern research has not ruled out that kind of repeat. The 1944 rupture appears to have occurred along a fault embedded in the complex system of old rift structures beneath the St. Lawrence. Stress studies suggest that nearby faults were not meaningfully relaxed by the 1944 event. In plain words, the system vented a bit of pressure. Much of it remained. When the April 2026 Shoreville shock struck further up the same broad seismic zone, and when the January Aurelia shock appeared in a quieter band to the west, both events added to the long-running diary of a landscape that is not finished adjusting. The magnitudes were small, the context is not, and running through all of this is a deeper scar, far older than any of these earthquakes. The Western Quebec seismic zone has a personality, long, quiet stretches, steady background tremors too small to feel, sudden, disproportionate shocks that shake an enormous region in a single burst, then quiet again, then another burst. Seismologists do not call this a cycle in the strict sense. Earthquakes in intraplate settings do not obey neat schedules, but the pattern across the last 3 centuries is striking enough to deserve close attention. Start with what is known. The 1935 Temiskaming shock reached magnitude 6.1. The 1944 Cornwall-Messina shock reached magnitude 5.7 to 5.8. The 2010 Val-des-Bois shock reached magnitude 5. The 2013 Ladysmith shock reached magnitude 4.7. Smaller events happen every few weeks in the background. Between 1980 and the year 2000, the Western Quebec seismic zone produced at least 16 earthquakes above magnitude 4. On average, the zone registers a seismic event roughly every 5 days. That is not the signature of a dormant region. That is the signature of a continuously creaking system that occasionally snaps hard. The spatial pattern is also revealing. Research has shown that earthquakes here tend to cluster along two broad bands. One runs northwest to southeast, roughly parallel to the direction of the ancient rifting that created the Ottawa-Bonnequiere-Graben and the Timiskaming-Graben. The other parallels the Ottawa River itself, following the mapped faults of the same rift system. A smaller cluster sits near Maniwaki, to the north. Another sits near the Adirondack Highlands to the south. All of these clusters share a common ingredient: old, deep fractures in the crust, aligned in exactly the orientation that lets them slip under the modern stress field. Here is what makes this zone unusual compared to other intraplate regions of eastern North America. Its maximum observed magnitude is higher, its clusters are better defined, and its largest earthquakes are concentrated along the younger of the two ancient rift systems. The Ottawa-Bonnequiere-Graben, formed in the late Proterozoic and possibly reactivated during the opening of the Iapetus Ocean hundreds of millions of years ago, has hosted the largest known events. The older metasedimentary belt has hosted smaller ones. This pattern matters for the April 2026 Shoreville shock. The epicenter sat inside the broader rift corridor that has produced most of the zone's significant earthquakes. It was small, it was shallow, it was consistent with a minor fault slip along an old structure, and it came from the same general system that, a few decades from now or a few centuries from now, is statistically most likely to host the zone's next significant shock. Modern researchers also watch this zone for a different reason. Because its clusters are distinct, they give scientists a chance to test ideas about stress transfer. When one fault slips, does it load the next one? Does the next quake happen nearby or far away? A 2023 study in the Canadian Journal of Earth Sciences argued that only the 1935 Temiskaming event caused extensive positive Coulomb stress change on its receiver fault, making that fault more likely to fail in the future. That is a specific concrete concern backed by data. A quiet interior is not a silent one, and beneath this seismic zone runs a much older track of heat and ancient pressure. It came from the Mantle, and it crosses directly under Ontario and Quebec. About 125 million years ago, a column of unusually hot rock rose through the Mantle beneath what is now northern Ontario. Scientists call this kind of feature a hot spot. The mantle plume beneath it did not move, but the continent above it did. As North America slowly drifted southwest across the Mantle, the hotspot burned a trail of thermal and mechanical damage across the base of the crust. The result is a line of features stretching from the New England region of the United States, under southern Quebec and eastern Ontario, out beneath the Atlantic seafloor, and eventually to the Great Meteor Seamount far east of the Gulf Stream. Geologists call it the Great Meteor Hotspot Track. Most people in Ottawa, Montreal or Toronto have never heard of it, but a growing body of research suggests that its ancient heat still matters today. A major study published in the Journal of Geophysical Research in 2007 by Ma and Eaton examined the relationship between the Western Quebec seismic zone and the mapped path of the Great Meteor Track. The authors found that modern seismicity in the zone clusters along a band roughly 160 kilometers wide and 500 kilometers long, extending from the Adirondack Highlands to the Laurentian uplands. That band overlaps the projected surface trace of the hotspot track. Their conclusion was careful but clear. The long-term thermal and mechanical effects of the passing mantle plume appear to have left the crust in this corridor more prone to earthquakes than the surrounding shield. Subsequent work has refined this picture. A 2018 abstract from the American Geophysical Union noted that earthquakes in the western Quebec seismic zone cluster in two elongated bands, one oriented northwest-southeast where most local events occur, and another paralleling the Ottawa River along the mapped faults of the Graben. Since the mid-1970s, scientists have suggested that these zones sit above a crust that was thermally weakened by the ancient hotspot. Here is how this mechanism works in simple terms. As the plume burned under the crust, it heated the lowermost layers, softened them, and possibly melted small volumes of rock. It left behind zones of altered mineralogy and deep weakness. When the plume moved on and the rock cooled, those zones did not fully recover their original strength. Hundreds of millions of years later, when the continent was pushed by Atlantic ridge push and lifted by glacial rebound, those old weaknesses became the first places the crust broke. The Western Quebec seismic zone is not the only intraplate region that lies above an ancient hotspot track, but it is one of the best studied. Its earthquakes are not random. They align with crustal structures that record ancient heat, ancient rifting, and ancient fractures. And every new shock in the zone, including the April 2026 Shoreville event, fits into this broader architecture. What does this mean for modern Canadians? It means that the small tremors being felt around Ottawa, Orillia, Shoreville, Val-des-Bois and Ladysmith are not random bursts of noise. They are releases along a long narrow corridor of old crustal scars, influenced by an ancient plume, loaded by rebound, and squeezed by distant plate forces. This corridor is one layer of the puzzle. There is another, even older and stranger, and it involves a catastrophe from space. Imagine running a blowtorch slowly along the underside of a thick sheet of steel. The metal does not melt, but the heated path changes. It becomes softer, more fractured, more prone to bending in certain directions. Decades later, if you press on that sheet from the sides, it will start to fold along the path the torch travelled. This is how a mantle plume affects a continent. When the great meteor hotspot heated the base of the crust beneath what is now eastern Canada, it did not create volcanoes at the surface. The crust was too thick, the plume not quite strong enough, and the movement of North America spread the effect across a long path. What the plume did do was thermally alter the rock below the crust, producing zones of modified density, modified rigidity, and modified fluid content. Those zones are now frozen into the modern lithosphere. They cannot be seen from the surface. They show up in gravity maps, magnetic anomaly maps, and deep seismic tomography. Research papers have linked the Western Quebec seismic zone explicitly to these deep features. The 1981 study on the zone's characteristics noted that its earthquakes correlate with gradient zones around two prominent anomalies in the smoothed Booga gravity field. In plain terms, the quakes cluster where the density of the crust changes sharply. Those density changes trace ancient structural boundaries, some of them related to the hotspot track, some of them related to earlier mountain-building events during the Grenville orogeny more than 1 billion years ago. The 2007 JGR study by Ma and Eaton went further. Using earthquake location data and tomographic models, the authors argued that the mid-crust beneath the Western Quebec seismic zone shows evidence of thermal alteration consistent with the passage of the Great Meteor Plume. They suggested that the plume-altered crust now acts as a long-term zone of mechanical weakness, concentrating stress from distant sources into failures along old fault structures. This is a slow, deep process. It does not feed directly into any single earthquake. It shapes the stage on which earthquakes occur. Here is the analogy. Picture a wooden table covered by a heavy tablecloth. The cloth is the modern crust. Underneath, along one line, someone has weakened the wood by boring small holes. You cannot see them. But if you press on the table from both ends, It will bend first along that line of holes. Every crease in the tablecloth above lines up with those holes. The Ottawa-Bonacher Graben, the Timiskaming Graben, and the various faults that cluster along the Ottawa Valley are the creases. The great meteor plume is the bore. This is also why the modern earthquakes in the western Quebec seismic zone tend to be shallow, relatively small and tightly clustered. They occur in a specific thickness of crust, along specific orientations, in specific corridors. Random seismicity in intraplate regions does not usually behave this way. When you see patterned behavior over centuries, you're looking at deep structure controlling surface events. The April 2026 Shoreville shock occurred along this patterned corridor. So did the 1935 Temiskaming quake. So did the 2010 Val-des-Bois quake. These are not coincidences. They are signatures. The structure shaped by the plume is one kind of ancient wound. There is another kind, more sudden, more violent, more visible from space. Drive northeast from Quebec City along the north shore of the St. Lawrence River, and you will enter one of the most beautiful regions in Canada. Rolling farmland, high cliffs, a wide, cold river, the Charlevoix region. Tourists visit for the scenery, geologists visit for the scar. About 350 million years ago, a meteor about 2 kilometers across struck this coastline at high speed. The impact released energy measured in the tens of thousands of megatons of trinitrotoluene. It created a crater roughly 54 kilometers wide. It shattered the bedrock to enormous depth. It twisted, broke, and melted rock across a zone that is still visible today from the air. Erosion has flattened much of the crater rim. Modern farms sit inside what was once the impact floor, but underground the structure is still there, dense, fractured, weakened, and the faults that run through it have not gone back to sleep. This is the Charlevoix seismic zone. It is one of the most active intraplate earthquake regions in North America. It also intersects one of the strongest stress fields in eastern Canada, where the St. Lawrence Rift system, ridge push from the Atlantic, and post-glacial rebound all converge. The result is a region that regularly produces moderate to large earthquakes, in contrast to the surrounding shield. On February 5, 1663, a catastrophic earthquake tore through this zone. Surface effects were described by Jesuit missionaries and early settlers. The ground cracked open. Landslides cascaded from cliffs. Rivers changed course. Eyewitnesses reported ice in the St. Lawrence splitting apart. Geologists today estimate the magnitude at approximately 7. Direct measurement is impossible because seismographs would not exist for another 2 centuries. The Charlevoix 1663 event is still one of the largest earthquakes in the recorded history of eastern North America. More shocks followed in 1791, 1799, 1870, and 1925. The 1925 event near Cap-à-Lael reached magnitude 6.2. Damage was recorded along both shores of the St. Lawrence. Reports came in from hundreds of kilometers away. Modern Canadian seismographs catch small earthquakes in the Charlevoix zone almost every week. Many are so small that only the instruments notice. Occasionally the zone produces moderate shocks in the magnitude 3 to 4 range, which can be felt across Quebec City and parts of the Charlevoix coast. The long-term pattern is similar to the western Quebec seismic zone. Steady background activity, occasional moderate events, rare but powerful large shocks. What makes Charlevoix especially striking is its direct link to the impact structure. Research has shown that seismic activity within the zone is concentrated along old rift faults that pass through the weakened crater rock. The crater did not cause the faults. The faults already existed, related to the ancient St. Lawrence Rift, but the impact shattered the region around them, making them more slippery, more prone to release, more active today. This is one of the few places on Earth where an ancient meteor strike and modern earthquake activity are clearly connected. The Charlevoix zone is not linked to the January Aurelia shock or the April Shoreville shock directly, but it belongs to the same family of intraplate danger. Canada is not a single seismic story. It is a chain of them, and one of them crashed from the sky. The winter of 1663 opened quietly in the French settlements along the St. Lawrence River. Then, at about 5:30 in the afternoon of February 5th, the sky seemed to roar. Houses rocked, church bells rang without being touched. Trees swayed in still air. The ground itself appeared to heave and fall like the waves of the sea. The Jesuit missionaries of New France kept careful records. Their accounts, preserved in the Jesuit Relations, remain one of the most detailed early descriptions of a major North American earthquake. They wrote of a shock so intense that the ground at first was said to seem like liquid. Cliffs collapsed into rivers, rock falls buried valleys. Mountains, the missionaries wrote, appeared to move from their foundations. Rivers changed their courses in places. New lakes formed temporarily where dams of landslide debris blocked old streams. The shaking lasted, by their account, most of half an hour in diminishing intensity. Aftershocks continued for months. Modern scientists have estimated the magnitude of this event at about 7. Based on the spatial extent of reported effects, the scale of landslide and liquefaction features still visible in the geological record and comparison with later well-measured Canadian earthquakes. There is uncertainty in the estimate, but the lower bound alone puts it well above any earthquake recorded in modern Canadian history. The Charlevoix 1663 event stands out for several reasons. First, no human lives are known to have been lost directly by the quake in New France, primarily because the settler population was very small and widely scattered, and most lived in wooden buildings that flexed instead of collapsing. But the geological damage to the landscape was extreme. Entire hillsides slid into the St. Lawrence, cliffs shattered, tributary rivers choked with debris. Indigenous communities in the broader region also experienced severe shaking, although direct casualty records from that period are incomplete. Second, the event revealed the long-term seismic capacity of this zone. A region that had experienced no recorded damaging earthquake in living settler memory suddenly produced a magnitude approaching 7. If the Charlevoix zone can do that once, it can likely do it again. Third, the location of the epicenter was within or very close to the ancient meteor impact structure that defines the zone. Subsequent research has repeatedly found that earthquakes in Charlevoix cluster inside or on the edges of the crater, along rift faults that pass through the weakened impact rock. The 1663 event fits this pattern. Modern Quebec is a different place from the tiny colony of 1663. The population of the province now exceeds 8 million. Quebec City alone has more than 500,000 residents. The Greater Charlevoix region contains towns, highways, bridges, a major hydroelectric plant on the St. Lawrence, and a popular tourism corridor. A repeat of the 1663 earthquake today would be a disaster on a scale Canada has never experienced. Canadian seismic hazard maps take the Charlevoix zone seriously. Provincial emergency planners do as well. But the public awareness of this risk remains modest, especially compared to the attention directed at the Pacific coast. The 1663 event is a reminder that eastern Canada's seismic history is deeper than the modern instrumental record. Entire generations can pass between large shocks. Then a region that seems tame becomes, for half an hour, the most dangerous place on the continent. And there is another dangerous zone, this one offshore, where the shaking hides a second killer. November 18th, 1929, a clear autumn evening on the southern coast of Newfoundland. Fishermen were cleaning boats, families were finishing dinner, lamps lit the windows of small villages along the Burin Peninsula. Then, at 5:05 in the afternoon, the seafloor 260 kilometers to the south snapped. A magnitude 7.2 earthquake ruptured beneath the Grand Banks of Newfoundland, along the edge of the continental shelf. At that depth and that distance, the shock was felt as a strong rolling motion across Atlantic Canada. Plates fell off shelves, clocks stopped, but there was no immediate damage in most coastal villages. The shaking faded. People went back to their evenings. Then, about 2.5 hours later, the ocean itself arrived. The earthquake had triggered a massive underwater landslide on the continental slope. A wall of sediment, thousands of cubic kilometers in volume, collapsed downward into the deep Atlantic. The movement of that sediment generated a tsunami. The wave moved outward across the Atlantic at hundreds of kilometers per hour. It lost height as it travelled, but it retained enough energy to curl into the shallow bays of the Burin Peninsula and strike coastal Newfoundland with catastrophic force. In some narrow inlets, the wave reached heights of 7 meters, more than 20 feet. Boats lifted from their moorings and smashed into houses. Entire buildings were torn from their foundations. Wooden homes slid into the sea. Families were trapped inside as structures crumpled. 28 people were killed. Dozens more suffered injuries. Hundreds lost their homes in a region already living in tight economic conditions. This was the first and, to date, only confirmed fatal tsunami in modern Canadian history. The 1929 Grand Banks earthquake also became a turning point in scientific understanding of offshore earthquakes. Researchers noticed that transatlantic telegraph cables lying across the continental slope had snapped one after another in precise timing. By reconstructing the sequence, scientists could measure the speed and distance of the underwater turbidity current generated by the landslide. It was one of the first direct measurements of such a flow. The finding revolutionized modern sedimentology. For Canada, the human lesson was harder. A rupture far out at sea, in a region where almost nobody expected a damaging earthquake, had produced a disaster that killed people in dozens of small villages along the coast. The shock itself had not been catastrophic. The wave it unleashed had been. Newfoundland, Nova Scotia, New Brunswick and Prince Edward Island all sit near offshore fault systems and unstable portions of the continental shelf. Canadian seismic hazard assessments now include tsunami scenarios for the East Coast, though they receive much less public attention than the tsunami threats tied to Cascadia in the West. The mechanisms differ. The possibility does not. A repeat of the 1929 event in the present day would still be dangerous. The coastal population is larger, tourism is heavier, infrastructure is more exposed. Early warning for an offshore landslide-triggered tsunami is difficult, because the initiating event can be partly submarine and partly tectonic, with only minutes between the cause and the arrival of the wave. The Grand Banks tsunami reminds us that Canadian seismic risk is not confined to the interior or the Pacific coast. The ocean floor, too, can slip, and when it does, the sea remembers. Now turn west. Because what has scientists most deeply worried is not the East Coast, It is a silence along the Pacific that has lasted more than 300 years. Walk through downtown Montreal and you'll see a beautiful skyline of stone and brick, 19th century churches, early 20th century office blocks, historic warehouses along the port. Much of this architecture was built before the word seismic meant anything to Canadian engineers. The same is true in Ottawa, Quebec City, Kingston and Cornwall. Much of eastern Canada's built environment rose during decades when earthquakes were treated as someone else's problem. That assumption is now the weak point hidden inside every old building in the region. Unreinforced masonry is the most dangerous kind of construction during an earthquake. Brick walls without internal steel, stone facades held up mostly by gravity, chimneys stacked on top of roofs with little more than mortar and weight. During strong shaking, these structures do not flex, they crack, they peel, they fall. A 1994 study in the Canadian Journal of Civil Engineering by Bruno and Lamontagne examined damage from 20th century earthquakes in eastern Canada. They focused on the seismic vulnerability of unreinforced masonry buildings. Their conclusion was direct. Even the moderate earthquakes of the 20th century, the magnitude 5 and magnitude 6 events, had produced clear patterns of masonry damage across affected cities. A larger earthquake in the modern population centres would produce significantly worse outcomes. Modern building codes have improved over time. After the 1988 Saguenay earthquake, which reached magnitude 5.9 and was felt across eastern Canada and the northeastern United States, Canadian seismic codes were strengthened. New construction in high-risk zones now incorporates steel frames, reinforced concrete, and structural detailing intended to resist lateral motion. Hospitals, schools, and critical infrastructure built in recent decades meet tougher standards than anything from the early 20th century. But most of the building stock is older than the new codes. A significant fraction of schools in Quebec and eastern Ontario date from the 1940s, 50s and 60s. Many older hospitals were constructed well before modern seismic detailing. Bridges span the St. Lawrence and the Outaouais, some of them decades old, some retrofitted, some not. Dams along the Ottawa River generate electricity for millions of homes. Pipelines carry gas and oil across ancient fault corridors. Every one of these assets has its own performance envelope. Every one of them faces a shaking hazard that is modest in normal years and potentially severe in rare ones. Here is the uncomfortable arithmetic. The Western Quebec seismic zone can produce a magnitude 6 plus event, as it did in 1935. The St. Lawrence corridor can produce a magnitude approaching 6, as it did in 1944. The Charlevoix zone can produce a magnitude approaching 7, as it did in 1663. If any one of those possibilities occurs in the current century, the shaking will reach cities that have grown dramatically since those historical events. The April 2026 Shoreville shock was a reminder of location. The January Aurelia shock was a reminder that stress is spread across the region. Neither was a threat to a single building, but both occurred inside the broader architectural vulnerability that Canadian engineers have been studying for decades. Seismic retrofit programs in eastern Canada have been modest compared to those in British Columbia. Funding is limited. Awareness is uneven. For most residents, earthquake preparedness is a concept from television coverage of other countries. For most owners of 19th century stone buildings, reinforcement is a cost without an obvious reward. A magnitude 4 tremor does not expose this vulnerability. A magnitude 6 would. And the history of the region shows that a magnitude 6 is not an abstract scenario. It is a recorded event. The next layer of the risk has to do with how the shaking itself travels. An earthquake is a package of energy, but how that energy reaches a city depends on what the energy travels through. In eastern Canada, the travel is efficient, dangerously efficient. Start with a simple question. Why does a magnitude 5 in the Pacific Northwest affect a few dozen miles, while a magnitude 5 in eastern Canada affects hundreds? The answer is the difference between two very different kinds of crust. West of the Rockies, the ground is broken. Active faulting, young volcanic activity, and a dense network of moving tectonic blocks have left the crust of British Columbia, Washington, Oregon, and California filled with discontinuities. Water fills many of those cracks. Sediments overlie the hard rock. As seismic waves travel through this fractured, fluid-rich, layered landscape, they lose energy quickly, dampened, absorbed, scattered. Within a few hundred kilometers, only a small fraction of the original energy remains. East of the Rockies, especially under the Canadian Shield, the ground behaves almost exactly the opposite. The bedrock is old, cold, dry, and continuous. It has been stable for hundreds of millions of years. Seismic waves pass through this crust with very little loss. A magnitude 4 earthquake in Quebec can be felt in Toronto. A magnitude 6 earthquake in the Ottawa Valley can rattle windows in Washington, D.C. The energy does not care about provincial borders. The rock simply does not stop it. Seismologists describe this behavior as low attenuation. In plain terms, the eastern Canadian crust is acoustically excellent. It transmits, it resonates, it extends the reach of any earthquake. Add one more factor. Intraplate earthquakes in eastern Canada tend to occur on faults with high stress drops. When they slip, they release energy sharply rather than gradually. That produces higher frequency shaking, which affects small and medium buildings more strongly than long, slow waves. Chimneys, walls, older masonry structures. These are exactly the parts of a building most likely to fail under the kind of motion generated by an eastern Canadian rupture. When scientists study how a given earthquake will affect people, they use something called intensity. Magnitude measures the total energy released at the source. Intensity measures how strongly the shaking is felt at a particular place. Taimi Mulder, an earthquake seismologist with Natural Resources Canada, has explained this distinction publicly many times. The most common misconception she sees in the public is the assumption that magnitude alone tells the full story. It does not. In the East, a moderate magnitude can produce a high intensity over a very large area. This is why the April 2026 Shoreville shock was felt from Ottawa to Montreal to Toronto. It is why the January 2026 Aurelia shock generated 2600 felt reports across southern and central Ontario within a few hours. It is why a magnitude 6 in the western Quebec seismic zone would be felt intensely across multiple major Canadian cities at once. Canadian building codes now account for this. Eastern seismic hazard maps incorporate low attenuation. Modern hospitals in Ottawa and Montreal are designed for it. But older structures are not protected, and millions of people live in them. A magnitude 4 in eastern Canada is an alert, not a warning. A magnitude 6 would be a warning. And the rock that makes these small tremors reach so far is also the reason a large rupture would feel so sharp. There is one more property of that ancient crust that makes the East different. The Canadian Shield is the largest expanse of exposed Precambrian rock on Earth. It extends across more than 8 million square kilometres, from Labrador to the Arctic, covering most of Quebec, Ontario, Manitoba, Saskatchewan, and parts of Alberta and the Northwest Territories. Its foundation rocks are between 1 billion and 4 billion years old. Glaciers scraped it flat. Forests, lakes and tundra cover it today. For geologists, the shield is a window into the deep history of the continent. For seismologists, the shield is the reason an earthquake in eastern Canada sounds different from an earthquake almost anywhere else. The key property is stiffness. The shield rock is dense, hard, and largely free of water. Seismic waves travel through it like sound waves through a struck tuning fork. They hold their energy. They radiate outward. They carry shaking across distances that would be impossible in softer terrain. This is why Eastern North American earthquakes have reputations for being felt much farther than their Western counterparts. The 1935 Temiskaming shock was felt across millions of square kilometres, from Manitoba to Virginia. The 1944 Cornwall-Messina shock was felt across large portions of 8 American states. The 1988 Saguenay earthquake reached magnitude 5.9 and was reported in Washington, D.C., more than 1,000 kilometers away. Even small shocks in the magnitude 3 to 4 range routinely produce reports from cities hundreds of kilometers from the epicenter. Picture the mechanism. Strike a bronze bell with a hammer. The sound radiates outward in all directions, clear and sustained. Now strike a wooden log. The sound dies within a few meters. The bell is the Canadian shield. The log is the fractured western crust. The same hammer blow, very different results. This is not just a pleasant metaphor, it is a practical concern. A magnitude 6 earthquake in the shield can generate intensities that cause damage hundreds of kilometers from the epicenter. Cities far from the rupture can experience shaking strong enough to crack walls, rupture gas lines, and trigger structural failures in older buildings. The footprint of damage in an eastern Canadian earthquake can be wide, even if the rupture itself is moderate. There is another effect. Because the shield carries high-frequency energy so well, the shaking tends to affect short structures more than tall ones. Bridges, small masonry buildings, chimneys, industrial equipment. This is the opposite of the pattern seen in very long-distance events through soft sediments, where tall skyscrapers sway most. Canadian researchers have been measuring these properties for decades. Seismic hazard maps for the Canadian Building Code incorporate the shield's transmission characteristics. Engineers designing dams along the Ottawa or St. Lawrence rivers use these maps. So do structural engineers working on nuclear power infrastructure and major bridges. But the public rarely hears about this. When a magnitude 4 tremor happens in Ontario and people in downtown Toronto feel their office chairs move, the news framing usually focuses on the fact that it was small. The more important story is that a small shock in the shield can reach a skyline 200 kilometers away. The April 2026 Shoreville shock radiated outward across the shield exactly as predicted. The January 2026 Orillia shock did the same. Both events demonstrated the efficiency of the transmission. Both events, in a sense, proved that the bell still rings. Which brings us to a question. If the bell is this sensitive and the faults still move, how far could the ringing travel from a truly large event? When the January 2026 Orillia shock struck at 10:59 at night, Earthquakes Canada expected some felt reports, a magnitude in the high 3 range at shallow depth in a populated part of southern Ontario. The staff was ready for a few hundred entries into the Did You Feel It system. Within hours, the count had climbed above 2,000. By the next morning it reached 2,600. The reports formed a pattern on the map that surprised even experienced seismologists. from Kingston on Lake Ontario, more than 200 kilometres to the east, from Kitchener, more than 150 kilometres to the west, from Belleville, from the Niagara Peninsula, from the outskirts of Toronto, almost 100 kilometres south. That felt footprint was large, disproportionately large. Then, in April, the Shoreville shock produced a similar pattern. Reports streamed in from Ottawa, Gatineau, Pembroke, Maniwaki, Montreal, and portions of the Greater Toronto area. A tremor centred in rural western Quebec had been perceived across a region several hundred kilometres wide. There are 3 reasons for this. First, the Canadian Shield carries seismic waves efficiently, as we've just seen. A shallow magnitude 4 in the Shield can generate perceptible shaking far from the source. Second, the depth of both events was relatively shallow. The Orillia quake occurred at roughly 5 kilometres. The Shoreville quake occurred at roughly 10 kilometres. Shallow earthquakes produce stronger surface shaking at close range than deep ones of the same magnitude. Combined with low attenuation in the Shield, a shallow shock has an exceptionally broad felt area. Third, population density in the affected regions is high. Millions of people live in the Ottawa Valley, the St. Lawrence Corridor, and the Greater Toronto Area. Even weak shaking experienced by millions of potential observers translates into thousands of reports on a national scale. This combination matters for reasons beyond statistics. Seismic networks depend heavily on felt reports to understand how shaking propagates across a region. Automated sensors give magnitude and depth. People give intensity. Together they build a 3-dimensional picture of the event. The Orillia and Shoreville felt patterns are now part of the long record of Eastern Canadian seismicity. They will be used to refine hazard maps, to improve ground motion models, and to calibrate the intensity predictions that go into building codes. There is also a psychological effect that scientists quietly consider. When small earthquakes are felt across huge regions, public perception of risk can rise faster than the actual hazard changes. People in Toronto who felt the Orillia shock called it an earthquake for weeks afterward. Many had never felt one before. In the hours after the Shoreville shock, reporters across Ontario and Quebec used the word earthquake, with a tone usually reserved for coastal events. The gap between perception and magnitude was real, and yet the perception carries a buried truth. Eastern Canada is in fact an earthquake region. It is not the West. It is its own system, with its own hazards and its own history of producing larger events when the conditions align. The Orillia shock was lightly felt. The Shoreville shock was minor, but both showed that the Canadian Shield, the ancient faults, and the rebound stress field are still coupled, still active, still sending signals. It is time to turn west, where the silence is different, and scientists are not reading small pulses. They are listening for the absence of something that should already have happened. Off the coast of Vancouver Island, beneath the cold, dark water of the Pacific, runs a fault about 1,000 kilometers long. It stretches from northern California, past Oregon, past Washington, past British Columbia. Where the heavier Juan de Fuca plate slides beneath the lighter North American plate, a boundary forms. Scientists call it the Cascadia subduction zone. By the rules of plate tectonics, this zone should be busy. Subduction zones elsewhere in the world produce earthquakes constantly. The coast of Japan records thousands per year. The coast of Chile does the same. Alaska, Indonesia, the Philippines. Every active subduction zone tends to hum with small to moderate shocks as the descending plate grinds its way downward. Cascadia does not hum. Cascadia is almost silent. Dr. Edwin Nissen, a University of Victoria Earth scientist who leads earthquake research at the university, has described this directly. He has told Canadian journalists that scientists are a little blind when it comes to Cascadia, because they have not been able to record many moderate earthquakes along the zone. He used an uncomfortable phrase. Cascadia is eerily quiet on the earthquake front. Silence in a subduction zone is not reassuring, it is alarming. A quiet fault is almost always a locked fault. Locked means the two plates are not sliding smoothly past each other. They are stuck. Friction holds them still. But the plates themselves never stop moving. 75 millimeters per year more or less, the Juan de Fuca plate continues its slow dive under North America. When the motion is blocked at the surface of contact, the rock behind the lock deforms. Strain builds. Every year that passes without a release adds to the total. Eventually something breaks, and when a locked subduction zone finally lets go, the resulting earthquake is not a magnitude 4 or 5, it is a magnitude 8 or 9. This is exactly what scientists fear is happening beneath Cascadia right now. The evidence for locking comes from several sources. Global positioning satellites measure tiny deformations of the Cascadia coastline that are consistent with strain building inland from the offshore fault. Coastal marshes preserve layers of sediment that show sudden episodes of subsidence, when previous quakes dropped the coastline by a meter or more. Buried forests along the Washington and British Columbia coasts record events when trees were abruptly killed by salt water, a pattern typical of rapid coastal sinking during a great earthquake. All of this points to the same conclusion. Cascadia has been locking and releasing for thousands of years. Great ruptures have occurred many times. The most recent happened on the evening of January 26, 1700. That date will come back in the next chapter. For now, what matters is what has happened since. 326 years without a major Cascadia rupture as of 2026. During that span, almost no moderate shocks have been recorded along the offshore portion of the fault. The plates have continued to move, the strain has continued to grow, the silence has only deepened. Scientists cannot predict the exact day the next rupture will occur, but they can estimate the odds, and those odds, published by the Oregon Department of Emergency Management, place the probability of a Cascadia event of magnitude 7.1 or greater at roughly 37% within the next 50 years. The silence is loud, and a small tremor in Ontario is not what keeps British Columbia's geologists awake at night. On the evening of January 26, 1700, at roughly 9 o'clock local time along the Pacific coast of North America, the Cascadia subduction zone released 3 centuries of stored strain in a single rupture. The break extended for about 1,000 kilometers. Estimated magnitude 9.0 or slightly larger. Estimated duration of rupture, several minutes of shaking. There were no instruments to record it, no written European accounts to log it in real time. The settler population had not yet reached that coastline. Indigenous communities along what is now the Washington, Oregon and British Columbia shoreline experienced the event in full. Their oral histories describe it vividly. Ground that rolled like the back of an animal, houses that collapsed, entire villages swept away by a flood that came from the ocean shortly after the shaking ended. That flood is the most telling part of the record. A Cascadia rupture lifts the sea floor by several meters along its length. When the floor moves, the column of water above it moves. That displacement creates a tsunami. In 1700, the tsunami would have reached the coastline within minutes on the Canadian and American sides. Low areas were inundated. Villages on tidal flats were destroyed. Cedar trees in coastal marshes were killed in place by sudden saltwater flooding, creating the buried ghost forests that modern scientists have dated by their tree rings. The tsunami did not stop at the North American coast. It crossed the Pacific. In Japan, about 10 hours after the rupture, a series of strange waves struck the eastern coastline. Japanese officials and villagers kept written records of what they called an orphan tsunami, a wave without a local earthquake to explain it. The records included date, time, wave heights, and damage. These accounts were preserved in provincial archives. 300 years later, geophysicists Brian Atwater and Kenji Satake, working with colleagues, used those Japanese records to solve a scientific mystery. By combining the arrival times and heights of the Japanese tsunami with the carbon dates of ghost forests along the American and Canadian coasts, they calculated backward. The numbers pointed to a single event. Late in the day of January 26, 1700 Pacific Standard Time, magnitude 9, Cascadia. This was one of the first times in history that the source of a great earthquake was reconstructed from a tsunami record on the opposite side of the ocean. The discovery transformed Pacific Northwest seismology. Before it, many scientists still doubted that Cascadia was capable of a great rupture. After it, the evidence was overwhelming. The written Japanese records, the buried ghost forests, the sediment layers in coastal marshes, the oral histories of indigenous nations, everything agreed. The Cascadia subduction zone produces great earthquakes, and one had occurred about 300 years before the research was published. Since that discovery, Canadian and American scientists have worked continuously to improve the hazard picture. Drilling programs have sampled turbidite deposits on the Pacific floor, muddy undersea landslides triggered by past great quakes. The record shows about 40 of these over the last 10,000 years, suggesting an average spacing of roughly 200 to 500 years between great ruptures along the full zone, with substantial variation. The last one was 326 years ago. The next one is not scheduled, but its physical possibility is fully established by the record, and the evidence continues to sharpen today. The most surprising thing about the 1700 Cascadia earthquake is that its existence was confirmed using records from a country on the other side of the Pacific. To understand why this matters, consider what was available before. In the 1980s, there was still genuine scientific debate about whether Cascadia could produce a magnitude 9 earthquake at all. The offshore fault did not show much seismic activity. The geological record on land was unclear. Some researchers argued that the subduction zone might slide without locking at all, producing no great earthquakes. Others argued that it was locked and dangerous. The evidence on either side was mixed. Then researchers began finding odd features along the Pacific Northwest coast. Brian Atwater, working with the United States Geological Survey in Washington state, identified layers of sand deposited on top of soil in coastal marshes. The pattern suggested a sudden drop in land elevation and the inrush of a tsunami. He found similar layers up and down the coast, suggesting a single regional event. Carbon dating placed it around 300 years before the present. Cedar trees in the same marshes, killed in place by salt water, dated to approximately the same period. The fingerprints pointed to a large Cascadia earthquake, but the exact date remained uncertain. A rupture in 1690, in 1700, in 1720. Precision was out of reach. Then Kenji Satake of the Geological Survey of Japan turned his attention to a historical mystery on the Japanese side. Japanese records describe a tsunami that struck the eastern coast of Honshu on January 27, 1700 local time. The waves damaged villages in Iwate, Miyagi, Ibaraki, and other coastal provinces. No local earthquake had been recorded. Officials called it the orphan tsunami. Satake, working with Atwater and colleagues, hypothesized that the orphan tsunami was generated by a Cascadia event. Using tsunami propagation models, they calculated how long it would take for a wave generated off the Pacific northwest coast of North America to cross the ocean and reach Japan. About 10 hours. They worked backward from the Japanese records. The source earthquake would have occurred in the evening hours of January 26, 1700 Pacific Standard Time, with an estimated magnitude of approximately 9. The pieces fit together: the ghost forests along the Washington and Oregon coasts, the sand layers in coastal marshes, the oral histories of the Maka, the Quileute, the Ho, the Yurok, and other coastal nations. The tsunami records preserved in Japanese provincial archives, every line of evidence pointed to the same night. The result was published in a series of scientific papers and later expanded into a book, The Orphan Tsunami of 1700, which has become a classic text in earthquake research. The methodology set a new standard. Great earthquakes can leave fingerprints in sediment, in trees, in oral traditions, and in records kept thousands of miles away. Combining these lines of evidence, scientists can reconstruct events that no seismograph ever recorded. For Canadian and American scientists, the 1700 reconstruction does two things. It confirms beyond reasonable doubt that Cascadia can produce magnitude 9 earthquakes, and it sets the calendar. The last one was 3 centuries ago. The accumulated strain along the fault has been building ever since. Every generation of researchers that picks up this work finds new layers of detail. Some of those layers point to smaller events that do not rupture the full zone. Some point to great events that do. The debate now is not whether Cascadia can rupture, it is how the next rupture will look, and new research is sharpening that question in uncomfortable ways. Along the Pacific coast of British Columbia, the Juan de Fuca plate descends beneath North America at roughly 4 centimeters per year. In some places the descent is smooth. The two plates slip past each other in a slow, steady motion. Stress does not accumulate in those areas. Great earthquakes do not originate from them. In other places the descent is not smooth. The plates are fused together by friction. The upper plate bends, the lower plate drags, and strain builds along the boundary. Scientists call these places locked zones. They are the dangerous parts of a subduction zone. The locked zones of Cascadia have been mapped using global positioning satellites. By measuring tiny movements of the coast, sometimes millimeters per year, researchers can model where strain is accumulating. The maps show a significant locked region offshore from Vancouver Island, extending along much of the British Columbia coast, with variations in the degree of locking along different segments. A recent study of the Cascadia subduction zone has added new detail to this picture. In 2026, researchers led by Malene Kidiwela published work in the journal Science Advances, using 13 years of ground motion data from seafloor observatory sensors to analyse how locked different parts of the fault really are. They found that while the northern part of the zone appears locked and quiet, other sections exhibit more complex behaviour, including evidence of fluid movement along the fault and areas that may not be fully locked. This is a subtle but important finding. Fluids, when present in a fault zone, can change how stress accumulates and releases. They can lubricate slip. They can also allow small, slow-slip events that release strain gradually without generating a large earthquake. The Kiddiwela study suggested that the picture of Cascadia is more complicated than a simple locked versus unlocked dichotomy. The implications run both ways. On one hand, areas with fluid activity might release strain through slow slip, reducing the worst-case scenario for those specific patches. On the other hand, the existence of fluids does not eliminate the hazard from the parts of the fault that are strongly locked, and those parts, according to all existing models, remain capable of producing a great earthquake. A related study from April 2026, reported by FIS.org, described a newly identified tear in the subducting plate off Vancouver Island. Briefly, some commentators wondered whether this tear indicated that Cascadia was shutting down, lowering the regional risk. The research team, including UVIC scientist Edwin Nissen and colleagues, pushed back on that interpretation. The tear may influence where ruptures start and stop, or how far they propagate. But it does not remove the underlying seismic hazard. In practical terms, the hazard model for British Columbia has not fundamentally changed. The coastline is still positioned directly above a subduction zone capable of great earthquakes. A large event would still produce strong shaking across Vancouver Island, the British Columbia lower mainland and inland cities. A tsunami would still threaten coastal communities within minutes of a rupture. This is why Canadian scientists do not breathe easier when a study reveals complexity in the fault structure. Complexity rarely reduces risk. It more often means that the shape of the next event is harder to predict, not that the event itself is less likely. The locked zone beneath Vancouver Island remains one of the most critical features on the Canadian seismic map, and the odds of its release are now being estimated in official provincial reports. Research over the past 2 years has complicated the standard Cascadia story in ways most members of the public have never heard. For decades, the dominant view was that Cascadia behaves like many other great subduction zones. Plates stuck, stress building, eventually a great rupture releasing that stress all at once. The 1700 earthquake was the reference event. Every coastal preparedness campaign, every hazard map, every provincial disaster report in British Columbia was built on top of this model. Then newer studies began to reveal that not all parts of the Cascadia fault behave the same way. A 2026 study published in Science Advances by Malene Kiddiwela and colleagues analysed ground motion data from seafloor observatory stations established along the fault. 13 years of continuous recordings made it possible to measure subtle ground vibrations that were previously missed. The analysis showed that different portions of the fault have very different characteristics. The northern section of Cascadia, offshore from Vancouver Island, appeared tightly locked and quiet. That fits the traditional picture. But in other sections, the researchers identified signs of fluid activity along the fault. Water rising from the descending oceanic plate was moving through the rock and affecting how the two plates were interacting. Fluids in a fault zone can do two things. They can weaken the rock, reducing friction and allowing slow seismic slip. They can also build up in isolated pockets, creating high-pressure zones that may eventually trigger seismic events when the pressure is released. The exact balance in Cascadia depends on local geology. Another finding from the same research team was evidence that parts of the fault surface were not fully locked. The fault appeared to be releasing some strain continuously through imperceptible motion. In other regions of the fault, the surface was still strongly locked, consistent with earlier models. What does this mean for the hazard? The researchers and their colleagues were careful. These findings do not indicate that the entire fault is now safe. large portions of Cascadia remain locked and are still accumulating strain. The presence of fluid pathways and partial slip does not change the long-term picture. The subduction zone can still rupture in a great earthquake. A published paper on FIS.org in April 2026 emphasized this point directly. Large earthquakes in Cascadia are determined by how strain accumulates and is released along the boundary between the plates. Studies show that parts of this boundary remain strongly locked, meaning that strain is still building and could be released in future large earthquakes. A related paper describing a tear in the subducting plate off Vancouver Island made the same point. The tear may influence where a future rupture starts or stops. It may change how far the rupture travels along the fault. It does not remove the threat. William Wilcock, a University of Washington oceanography professor and one of the scientists involved with the seafloor observatory work, summarized the scientific response simply. Finding this link between fluids coming to the shallow subduction zone is pretty unique, he said. It suggests that we need more instruments there, because there may be more going on than people have been able to figure out before. The Cascadia story is becoming more detailed, but not more comforting. A fault that is partially locked is still a fault that can rupture, and the implications continue to sharpen. In early 2026, a scientific finding about Cascadia briefly gave parts of the public a sudden sense of relief. News reports described a newly identified tear in the oceanic plate that is sliding beneath Vancouver Island. Some commentators, reading the story quickly, wondered whether this meant the subduction zone was shutting down and the risk of a great earthquake in British Columbia was lowering. The scientist who produced the research quickly pushed back against that interpretation. The finding itself came from recent seismic imaging studies along the Cascadia subduction zone, including the work reported on FIS.org in April 2026. Researchers used high-resolution techniques to produce detailed images of the descending Juan de Fuca plate beneath Vancouver Island. They discovered a tear in the plate, a discontinuity that divides the subducting slab into segments. A tear of this kind is not unique to Cascadia. Similar features have been identified in other subduction zones. What matters is what the tear does to the mechanics of future earthquakes. Here is the careful interpretation that researchers offered. A tear in the subducting plate can influence where a rupture begins or ends. It can affect how far a rupture travels along the fault. It can potentially change the shape of the released energy, but it does not eliminate the strain that is already accumulating elsewhere along the locked portions of the fault. The FIS.org article summarized this point clearly. The recent finding has important implications for seismic hazards in the region, which continue to be a major concern. Large earthquakes in the Cascadia subduction zone are determined by how strain accumulates and is released along the boundary between the plates and associated faults. Studies show that parts of this boundary remain strongly locked, meaning that strain is still building and could be released in future large earthquakes. In other words, Cascadia is not shutting down. Cascadia is more complicated than we thought. This distinction matters for provincial planners, for engineers, for insurers, and for residents of British Columbia. The 2026 Disaster and Climate Risk and Resilience Assessment, published by Climate Ready BC, explicitly modelled a magnitude 9 megathrust earthquake from Cascadia as one of the scenarios that could affect the province. The report noted that such an earthquake is one of the more likely major earthquake scenarios for British Columbia, highlighting important and less understood aspects of the risk. Those aspects include the difficulty of predicting exactly where the next rupture will begin, how far it will travel, and what its shaking footprint will look like. A tear in the plate adds to the uncertainty. it does not reduce the long-term hazard. For coastal communities on Vancouver Island, the new finding has practical implications. It suggests that some segments of the fault may rupture separately in smaller events, while others may rupture together in a full zone-wide event. The difference matters for emergency response planning. A segmented rupture might produce a smaller tsunami. A full rupture would produce a larger one. Canadian seismic hazard maps already incorporate these uncertainties, but the maps will be updated as new data arrives. Residents cannot rely on the tear as reassurance. The scientists involved in the research have been clear on this point. No single new finding changes the fundamental fact that the Cascadia subduction zone can produce a great earthquake, and the last one was more than 300 years ago. The probabilities, however, are explicit. Estimates of the odds of a large Cascadia earthquake within a defined time window are not speculation. They are published in official government documents. The Oregon Department of Emergency Management, on its public Cascadia subduction zone page, states that scientists currently predict there is about a 37% chance that a megathrust earthquake of magnitude 7.1 or greater will occur within the next 50 years in this fault zone. That probability reflects current research on the geological history of the zone, the recurrence interval of past events, and the time since the last great earthquake in 1700. The government of British Columbia has published its own assessment. In late 2025, the province released the Disaster and Climate Risk and Resilience Assessment through its Climate Ready BC program. The report modelled a magnitude 9 megathrust earthquake as one of the scenarios British Columbia should prepare for. It cited research suggesting that the probability of such an extreme event is between 2 and 10% within the next 30 years. Those numbers are lower for the full 9 magnitude scenario than Oregon's figure for the 7+ scenario, because a full zone-wide rupture is rarer than a smaller event on a portion of the fault. Edwin Nissen, quoted in the CBC coverage of that report, underlined that such earthquakes do not follow a regular schedule. Sometimes they happen in quick succession. Sometimes they happen hundreds of years apart. The statistical averages do not allow for precise prediction. They do allow for probability assessments, and the probabilities are not negligible. What would a magnitude 9 rupture do? The Weather Network, reporting on the Climate Ready BC assessment, described the modelled scenario. Minutes after a massive magnitude 9 earthquake strikes off Vancouver Island one summer day, thousands of British Columbians are dead or injured in the wreckage. Then comes the tsunami, then the aftershocks, then the chaos of collapsed infrastructure, severed communications, damaged bridges, broken water systems, and isolated coastal communities. These are not fringe predictions. They are the output of a provincial emergency management assessment, modelled by experts, reviewed by government officials, and published for public planning purposes. The report also noted a comparison. The 2004 Indian Ocean earthquake, which produced the catastrophic tsunami that killed more than 230,000 people across 14 countries, is listed as comparable to a Cascadia event in terms of its tectonic setting, length of rupture, and tsunami generation potential. That comparison is sobering. The Indian Ocean tsunami struck coastlines that were poorly prepared. Much of the death toll came from populations that had no warning system, no evacuation infrastructure, and no experience with large tsunamis. British Columbia has some of these advantages that the Indian Ocean coastlines did not. The province has an emergency alert system. Evacuation routes in coastal communities have been planned. Schools conduct drills. Municipal governments maintain disaster preparedness programs. The annual Great British Columbia Shakeout drill trains residents in drop, cover and hold-on procedures. But the underlying risk is real, and the province itself says so in its own documents. The Aurelian-Shoreville tremors in eastern Canada were small. The potential of a Cascadia rupture on the opposite coast is not. For Canadian seismologists, the two coasts represent different problems within a single national hazard picture, and the Pacific side is the one with the largest catastrophic potential. It is time to look at what a Cascadia event would actually do. Imagine a clear summer afternoon along the coast of Vancouver Island. A ferry is pulling out of Swartz Bay. A school class is on a field trip in Tofino. Fishing boats are working the waters off Ucluelet. Hikers are on the trails of Pacific Rim National Park. The sun is bright. The forecast is calm. Then the ground begins to shake. Not in a few sharp pulses, the way a short-duration earthquake does, but in a long rolling motion that lasts minutes. Not 10 seconds, not 30, minutes. This is a signature of a great subduction zone earthquake. In that time, buildings across southern British Columbia experience strong shaking. Older masonry cracks, unreinforced chimneys collapse. Bridges designed to a pre-modern seismic standard suffer damage to their approaches and piers. Highways buckle at bridge joints. Power substations shake loose. Rail lines warp. Cellular towers go offline as the grid loses power. That is the shaking phase. What happens next is why Cascadia is so dangerous. Along the coastline, the sudden motion of the seafloor displaces the water above it. A tsunami begins moving outward. Because Vancouver Island and parts of coastal British Columbia sit so close to the offshore rupture, the tsunami arrival time in some areas is measured in minutes rather than hours. There is no time for a detailed warning. Coastal residents in low-lying areas must evacuate on foot or by vehicle to higher ground immediately after the shaking ends. The height of the wave varies by location. Some shoreline configurations focus and amplify the wave. Others scatter it. In past Great Subduction Zone events, tsunamis in similar coastal environments have reached heights of 10 meters or more in narrow inlets. In British Columbia, communities in Tofino, Ucluelet, Port Alberni, and parts of the west coast of Vancouver Island are geographically exposed. Inland, the shaking radiates across the lower mainland. Vancouver, a metropolitan area of more than 2.5 million people, experiences strong motion. Newer buildings, designed to modern seismic standards, generally perform. Older buildings, particularly pre-code concrete frame structures and unreinforced masonry from earlier decades, are at higher risk. Even with excellent engineering, a great earthquake produces disruptions that cannot be fully engineered away. Water lines break, gas lines leak, electrical systems fail. The consequences extend beyond British Columbia. A Cascadia magnitude 9 rupture would also shake Washington State, Oregon, and Northern California. Seattle, Portland, and Sacramento would feel it strongly. Ports along the Pacific coast of North America would suffer damage. International shipping would be disrupted. Economic losses would reach into the hundreds of billions of dollars. Recovery would take years, possibly decades in the most affected communities. The Climate Ready BC assessment describes these outcomes in provincial terms. It is not a theoretical exercise. It is the scenario British Columbia's emergency management professionals are actively preparing for. And here is the part that Canadian scientists emphasize most clearly. The timing is uncertain. The event could happen tomorrow, or in 50 years, or in 200. Probability is not prediction. But preparation does not depend on exact timing, it depends on readiness. That is why Canadian agencies have spent recent years building a new system. A system designed to give residents of at-risk regions a warning that their grandparents would have considered science fiction. Seconds of advance notice before the shaking begins. That system is now live in parts of Canada, including eastern Canada for the first time. An earthquake is a race between waves. When a fault slips, two types of seismic waves travel outward from the rupture. The first is the P wave, or primary wave. It moves fast, between 6 and 7 kilometers per second, but it carries relatively little damaging motion. The second is the S wave, or shear wave. It moves more slowly, around 3 to 4 kilometers per second, but it carries most of the destructive shaking. This gap between the two waves is the basis of every earthquake early warning system in the world. If sensors can detect the arriving P wave, estimate the location and magnitude of the earthquake within a second or two, and transmit an alert before the S wave reaches a given city, residents can be warned to take cover. The warning time is usually short, a few seconds, 10 seconds. Occasionally, for very distant events, up to a minute, but those seconds save lives. Canada now has a national earthquake early warning system. It is operated by Natural Resources Canada. It was built with more than 400 seismic sensors distributed across regions of moderate to high earthquake hazard, including Western British Columbia, Eastern Ontario, and Southern Quebec. The system launched first in British Columbia in the spring of 2024. It expanded to Eastern Ontario and Quebec in the autumn of 2025. When sensors detect an earthquake of magnitude 5 or higher, shaking at intensity 4 or greater, the system automatically issues alerts. Public warnings go out through the National Public Alerting System, reaching compatible cellular phones, televisions, and radios. Critical infrastructure operators who have opted in receive direct notifications that can trigger automated actions. Surgeries can be paused. Bridges and tunnels can be briefly closed. Trains can slow. Gas valves can shut. The amount of warning time depends on distance. In British Columbia, for a quake occurring 600 kilometers offshore, P waves have been detected roughly a minute before S waves arrived inland. That would be more than enough time to duck under a desk. For earthquakes closer to population centres, warning times shrink. People near an epicenter may get no warning at all. This is exactly why the system's coverage was expanded to eastern Canada. The Western Quebec seismic zone and the St. Lawrence corridor are moderate hazard regions. A magnitude 6 rupture along an ancient fault in that zone would generate an alert through the new infrastructure, reaching residents of Ottawa, Montreal, Toronto, and points beyond. In late 2025, Canada announced the eastern expansion formally. The CBC, Canadian Press, and the Weather Network all covered the launch. The department also announced that earlier in the year, the only earthquake above magnitude 5 in Canada had been a magnitude 5.2 event off the coast of the Northwest Territories. That region has recorded only 3 quakes of that strength this century. The warning system is built for the kind of shock that does occur, just infrequently, and with unpredictable timing. There are limits. The system does not predict earthquakes. It detects them as they are starting. It cannot warn people closer to an epicenter than the sensors are. It only issues alerts for events expected to produce damaging shaking. Everyday small earthquakes do not trigger alerts, and the public alerts do not guarantee that everyone will respond in time, because habits, attention, and circumstances vary. But the system is a leap forward in Canadian public safety. and one of its most important new regions went online just months before the April 2026 Shoreville shock. Canadians along the Pacific coast have understood earthquake risk for a long time. Drills in schools, fasten bookshelves in homes, go bags beside the door, tsunami signs along highways. For decades, preparedness in British Columbia has been a cultural habit. Eastern Canada has not had the same relationship with earthquakes, and the delay in building an early warning system for the region reflects the history of that relationship. Hazard assessments in Canada rank British Columbia as a high-risk region for damaging earthquakes, with the Cascadia subduction zone as the major concern. Eastern Ontario and southern Quebec are ranked as moderate hazard regions. The difference is meaningful. The Pacific coast faces larger possible events at higher probabilities. The East faces smaller events historically, with lower probabilities but still real consequences. For years, that hazard hierarchy meant that investment in early warning focused first on the Pacific side. Natural Resources Canada, working with the United States Geological Survey and using their Shake Alert software as a foundation, built the Western system first. The British Columbia launch in the spring of 2024 reflected that priority. The Oregon Hazards Lab documented the process in detail, describing the over 400 seismic sensors deployed across British Columbia, Ontario and Quebec, with coverage along the Ottawa River Valley and the St. Lawrence Seaway on the eastern side. The eastern expansion came later. In the autumn of 2025, the government formally activated the Earthquake Early Warning System across eastern Ontario and southern Quebec. The CBC reported it plainly: a network of sensors that can provide crucial notice of a potentially serious earthquake is now up and running in Quebec and eastern Ontario. The department also said it was working on warning specific sectors so trains could be held, surgeries paused, and bridges or tunnels closed as appropriate. One practical reason for the sequencing: Eastern Canada earthquakes are less frequent than Western ones. The system needs dense sensor networks and proven algorithms to function. Installing and testing those sensors, writing alert logic tuned to Eastern Canadian crust, and integrating into the national public alerting system took time. Another reason is political and financial. Funding for this kind of infrastructure has to compete against many other public priorities. By late 2025, the Eastern system was live. By January 2026, the Aurelia shock tested public awareness of the new tools. The magnitude was below the alert threshold, so the system did not issue a public warning for that event. By April 2026, the Shoreville shock struck. Again, the magnitude was below the threshold. No alert. But both events served as reminders that the system is now watching in real time. This matters for the next event. Eastern Canada's seismic history shows that moderate events tend to be rare but possible, and larger events are much rarer but not impossible. The Temiskaming magnitude 6 in 1935 would today trigger the warning system immediately. Residents of Ottawa, Montreal and parts of the Greater Toronto area would receive alerts on their phones. Surgeries in progress would pause, bridges would be closed briefly, trains would slow. Those seconds do not change whether an earthquake happens. They change what happens during the earthquake, and understanding that small shift is part of a much larger picture. A picture in which Canada is sitting on multiple loaded systems, each with its own timeline, its own mechanism, and its own consequences. Step back from the individual events and the entire Canadian seismic picture comes into focus. It is not one story, it is several, braided together across a continent. On the Pacific coast, the Cascadia subduction zone lies silent and strained, accumulating centuries of motion that the last great rupture ended in 1700. Along the same coast, the Queen Charlotte Fault slips offshore of Haida Gwaii, producing its own earthquakes in a different geometry. Further north, seismicity in the Yukon and southern Alaska reflects motion along the Pacific and North American plate boundary. In the continental interior, the Canadian Shield transmits seismic waves with remarkable efficiency, turning every small tremor in the western Quebec seismic zone, the St. Lawrence Corridor, or the Charlevoix zone into a region-wide experience. Ancient rifts buried beneath the modern surface still slip. Post-glacial rebound continues to nudge them. Long-distance plate forces continue to squeeze them. On the east coast, the offshore margin of Newfoundland, Nova Scotia, New Brunswick and Prince Edward Island hosts its own hazard. The 1929 Grand Banks rupture and tsunami proved the region's capacity for disaster. Modern hazard maps include it. Public awareness is limited, but the geological reality is not. In the north, seismicity is less monitored, but still active. The magnitude 5.2 event off the coast of the Northwest Territories in 2025 was the only Canadian earthquake above magnitude 5 recorded in that year, and only the third such event this century in that region. Put these together and the picture is simple. Canada does not sit inside a single loaded spring. It sits on several, each with different release times, different magnitudes, different mechanisms. None of them can be precisely predicted. All of them produce effects that reach populated areas, and the modern Canadian monitoring infrastructure is the best the country has ever had. But it is still comparatively thin in many of these zones. Scientists at Natural Resources Canada, at universities like UVIC, Western University, the University of Toronto, McGill and many others are working steadily to refine what we know. Seismic networks have grown. Early warning systems have launched. Climate-ready assessments have been published. The map is sharper than it was 20 years ago. It will be sharper again 20 years from now. But the ground does not wait for science to finish its work. On an ordinary winter night in January 2026, the Orillia shock surprised people in southern Ontario who had never felt an earthquake. On an ordinary spring afternoon in April 2026, the Shoreville shock reminded people in Ottawa and Montreal that the valley is alive. Elsewhere, the Cascadia fault continued to accumulate strain. Elsewhere still, the Laurentide rebound continued its slow lift. Plate motions continued their slow push. Buried faults continued their quiet loading. 3 centuries since Charlevoix 1663, 3 centuries since Cascadia 1700, nearly a century since the Grand Banks 1929, 91 years since Temiskaming 1935, 82 years since Cornwall-Massena 1944. These are not distant numbers. In the timescales that govern intraplate and subduction zone earthquakes, they are recent. The country has no single fault to worry about. It has several, and they do not coordinate. The 2 recent Canadian tremors, small as they were, are part of this larger conversation between science and the ground. What they really signal is worth looking at closely in the final chapter. At the end of all this data, all this geology, all this history, there is one simple question left. What should the Orillia and Shoreville shocks mean to ordinary people? And what do they mean to the scientist watching the ground? Start with what the events were not. They were not precursors to an imminent large earthquake. Seismologists from Natural Resources Canada were explicit on this point. Marika Adams told the CBC that follow-up events of larger size in the Orillia region were highly unlikely. The causes of earthquakes in intraplate Ontario are less well understood than those at plate boundaries, but neither event showed characteristics that suggested a catastrophe was about to follow. What the events were instead was signal. Signal that the Canadian continental crust is not as silent as many assume. Signal that the ancient fractures of the Ottawa Valley and the buried weak zones of central Ontario still respond to the modern stress field. Signal that small shocks in regions of low seismic activity are still part of a long, large system that includes post-glacial rebound, ridge push, and hotspot track weaknesses. Signal that the early warning infrastructure, recently installed in the east, is ready to function when a larger event eventually occurs. Signal is not panic. Signal is awareness. Across the country, on the Pacific coast, a different kind of signal is present. There, it is the absence of small and moderate events that worries scientists. Edwin Nisson's eerily quiet phrase captures the unsettling nature of Cascadia. 7.5 centimetres per year of plate motion, year after year, with no visible release along the offshore fault for 3 centuries, means strain continues to accumulate. The odds published by provincial and federal agencies are not trivial. A magnitude 7.1 or greater in the next 50 years. A magnitude 9 remains possible in a smaller window. The last such event was 1700. The East Coast, the Grand Banks, the Yukon-Alaska corner, and the zones in between all contribute additional pieces to Canada's seismic portrait. The response is not paralysis. It is preparation. Canadian scientists, engineers, emergency managers and policymakers have spent decades building the tools of that preparation. The Canadian Earthquake Early Warning System, the Climate Ready BC disaster assessments, the updated National Building Code, the Great British Columbia shakeout drills, the eastern expansion of seismic sensors, the continuing research into rebound, hotspot tracks, ancient rift faults, and subduction zone behaviour. For individuals, the advice from Natural Resources Canada is straightforward. Know that your region may experience earthquakes, secure heavy furniture, prepare basic emergency supplies, understand what drop, cover and hold on means, sign up for public alerts, pay attention when an earthquake early warning reaches your phone. Seconds of notice can matter. For communities, the work is longer, retrofitting older buildings, updating critical infrastructure, planning evacuation routes, training emergency responders, building tsunami warning systems for coastal regions, investing in continuous seismic monitoring. The Shoreville shock came and went in a matter of seconds on April 14th, 2026. The Aurelia shock lasted about as long on January 27th, 2026. Both caused no damage. Both produced thousands of felt reports. Both reminded a country that the ground beneath it is not asleep. Scientists are on edge because they understand what these signals are part of. Ancient faults, Ice Age legacies, a silent Pacific fault with centuries of strain built up. Old wounds in a continent, a history of earthquakes that most Canadians have forgotten or never knew. The land remembers. It speaks in small pulses and occasionally in large ones. The recent Canadian tremors were small pulses. The work of the coming decades is to be ready if and when a larger pulse finally arrives. Because somewhere under Canada the stress never stopped building, and one day it will release again.